Welcome. This is our first Scale Warrior meetup, 2015. So Happy New Year. Thank you. This is the Scale Warrior Dome. I have a small story for you guys. A few years ago, 49ers, which used to have a stadium in the city, heard about us, about Aerospike, and they found out what we were doing. They were very impressed. You know, high performance, low latency, infinite scale, very impressed with us. So they started calling us saying, hey, please move the company to the city. We'll have more audience there, more seats. And we've been talking to them, and then finally Jet broke down and said, hey, we just can't get you guys over there. So how can we get back to the South Bay? So we went to the NFL, got them to host the Super Bowl next year here, and found them a stadium here, very close to where we are. And you're welcome. And so next year we'll have the Super Bowl here, and hopefully we'll keep the Super Bowl with the San Francisco 49ers. But the most important thing, that's not very important. This is the most important thing. You guys are all Scale Warriors. Very excited to see you guys here. This is where it all happens, between here and the office in Bangalore. We build a product which low latency, extreme scale, very high performance that you'll hardly find anywhere. So enough of me talking. I'd like to introduce Ronen, who's a colleague. I've known him for over 8 years. He's going to talk to us about some technology which has been lying to us for a long time. I'm very excited to hear what that is. Ronen, go ahead.
Hello, people. Alrighty. Hey, I managed to log into my laptop. That's awesome. Is it supposed to be this loud?
It's perfect.
Awesome. All right. Should we go? Okay. Whoa, I got a slide up there. Okay, so the first thing, if you can't read this, my name is Ronen Botzer. If the shirt didn't give it away already, I work here at Aerospike. I'm one of the engineers. I'm working on the client-side engineering, mostly with getting all the dynamic languages to be as feature complete as possible, because we started with the serious languages first, and it's time for PHP, Node, Python, and the rest, Ruby, to catch up. So we're almost there with those, by the way. But if you have complaints, I'm one of the people you can throw your tomatoes directly at. I wanted to say thanks to Ed and Diana from South Bay PHP, which is the co-sponsor of the other meetup that's co-sponsoring us here, and then Claire from this meetup group, Scale Warriors of Silicon Valley. So just a tiny bit of background. I worked in a bunch of startups starting in '99 when I was still a student. First, I was an engineer sort of in the web team of a bunch of different companies. Then I moved to data engineering with an ad network in San Francisco, and later a social network. And then a mobile SDK vendor that's in town here called Accelerator. So I did that for about 5-6 years, messing around with Hadoop and databases at scale, doing data warehousing and OLAP and stuff like that. So I've sort of had experience with both those fields. My most previous startup fail was with a mobile parking startup called QuickPay. I was the architect there, and now I'm here. So yeah, that didn't work out as well. All right, so first thing, I gotta refer to the sort of abstract of this meetup talk. So I have a hard time staying serious. You probably noticed that the abstract is pretty goofy. There's a lot of sort of pseudo-relationship metaphors in there. Objects and relationships. Yeah, that's a really bad joke to try to pull for a full hour. So I'm going to drop it really quickly. I'll address it in one slide, and then we'll slide out of that metaphor space. So Most of the things I'm going to talk about, I've been personally guilty of doing it myself. Being a zealot, really believing in all sorts of technologies that don't necessarily work, and then finding the hard way that sometimes you got to like toss them out the window, even though everybody keeps telling you that this is the way you do things. All right, so the preamble. We're going to stick to the idiotic abstract style here. So your ORM is not really much different than having a crazy significant other. At least that's how it feels when you're stuck with it and you're really in the middle of production problems. People tell you that you need to go steady. So that's why you do it. And you sort of, nobody questions why that's supposed to happen. And a lot of people here may know sort of how we got to this state of like why this is the way you do things. But I'm going to do a quick review of the history of like why RDBMS and why ORMs seem to pop up everywhere. I'm going to skip straight to the one slide later. I'm married, by the way, so this is why I'm dropping this really quickly. So the verbs usually are, like the names for these ORMs are always really exciting. They're like, you know, active record or, you know, spring, storm. You know, connotes action and getting shit done. The problem is, you know, like having a crazy girlfriend, boyfriend, whatever you prefer. It's a lot of times more drama than action. When you start hitting serious bugs or weirdness in the ORM itself, when you start spending a lot of time fixing the ORM and dealing with bugs in it or rewriting it yourself because you can't even get to like, you can't figure out where, if the bug is on the application side or if the bug is in the ORM, that is not that fun and sort of a gigantic waste of time. Reasons why people stay stuck to their ORMs, kind of similar to being in a bad relationship also. You do it because you're supposed to do it and you don't know about an alternative. You do it because people will mock you for doing things not the right way, because there's, you know, a adult way of writing code. And like I said, I'm going to stop here because I'm approaching that acronym, FIMS. Does anybody know what that stands for? Anybody? Foot and mouth syndrome. Yeah, so I'm pretty good with that. So I'm going to, that's it. I'm going to drop that whole metaphor style. So we're going to move to the backstory of sort of how we got here. And basically how we got stuck with the notion that applications need to have an ORM layer above an RDBMS. Because that's, you know, sort of the given knowledge. All right, so we're going back as far as slightly before I was born, so that's a while. The prehistory is going to go over the history of like where do relational database management systems come from. They seem like they've been around forever, but they're actually at some point were a new and exciting technology that was solving like real world problems. So, you know, I took a bunch of graduate level classes about RDBMSs. I personally like them. I like the theory behind them. But that doesn't necessarily mean that they're the correct thing for every job. So in 1970, a guy named Edgar, I think he went by Ted, Codd, released a paper called the Relational Model of Data for Large Shared Data Banks. This was after a year before, while working at IBM, he had like another paper released internally, but this was sort of like the white paper that went out there that people read, people that read professional magazines were reading about. The guy was a pretty interesting dude and sort of maps in a way to like what a modern engineer feels like rather than an academic of his time. So he had a degree in math and chemistry before World War II started. He was a Royal Air Force pilot, so a pretty cool dude. Then he worked at IBM as a programmer, like the old school programmer, as in making sure that certain programs run at the correct time and the results go to the correct people, dealing with like whatever the hell technology they use then to load programs. So he didn't actually get his PhD until his mid-40s. He was in the US. He went to University of Michigan, which if anybody knows sort of about the history of database sort of advances, a lot comes out of that specific university. We had a coworker that came from IBM whose advisor was advised by Cod himself. So that little group there had a lot of influence over the research and the industry later. So after finishing his PhD, he moved to the IBM Research Center here in San Jose. And that's why that spot is where a lot of like the relational database technology and ideas come from. So it took him quite a few years to actually convince IBM to make a product based on his paper. It was mostly because, IBM was a sales-centric company, and the sales guys wanted to keep selling the product that was already selling. They didn't want to have an internal product compete with what was like a successful sort of sales line. So it took almost 4 years to get this implemented. It was in a system called System R, which actually took another 3 years until they could convince an actual business user to purchase the system. It included a query language called literally SQL, which was written by Donald Chamberlain and Raymond Boyce. If anybody knows normal forms and such, there's a normal form called Boyce-Codd normal form, and that's named after those two guys. System R later turns into SQL. I don't know. I have a problem with, by the way, how to say this. It's either SQL or SQL. I usually switch back and forth, so nobody throw stuff at me for that. So that came out in 1981, and then 2 years later it became DB2. Already a product that people are sort of familiar with. In 1977, some dude named Larry Ellison co-founds a startup called SDL. He read several years after this paper came out about the paper, and he was really excited about like the business applications of it. They moved faster than IBM. It only took him 2 years when they renamed themselves to RSI. They launched this database called Oracle, and yes, the rest is history. It had a query language called SQL, and it's stuck with us since then. At the same time that this is happening, during 73, 74, there's two researchers from UC Berkeley. Again, you probably heard of them, Eugene Wong and Michael Stonebreaker, that were working there and were talking to people at IBM. They get excited about the paper itself and sort of the initial work on System R, and they go back to Berkeley and start a project called Ingress. So in 74, actually, just as System R is coming out, Ingress comes out, the first prototype of it comes out. This is an open source product. Okay, so again, the way it links to us today, Berkeley is behind a lot of open source software. Sort of a lot of the notion of open source comes out of like sort of research that they work on, get graduate students to work on, and then just pump it out constantly. So Ingress actually was open source. I think the thing I read was like by 1980, there was like 1,000 copies of it deployed, which for them is a huge amount of deployments based on open source. It had a query language called Quell, which in hindsight was a bad decision, because in 1980, sort of just when Oracle and Ingress are starting to pick up speed, they both have about the same amount of market share. SQL is a lot more popular with people than Quell, and that is allegedly one of the reasons why Oracle sort of took off and Ingress kind of lost market share over time, where in the beginning they were kind of about 50-50 on deployments. So like he did many, many times, if you follow Stonebreaker, he starts a pattern here where he leaves to commercialize the product that he worked on at UC Berkeley. And after not succeeding too much with it, he comes back in 1985 and he starts working on a separate system based on sort of insights called Postgres. Again, probably a name you're familiar with. In 84, there's a team of ex-grad students that leave, that used to work on Ingress, that leave, and they start Sybase. The significance of Sybase, again, if anybody's worked with Microsoft products, you'll notice that there's a query language called T-SQL that they have in their database. And it's not by chance that it seems familiar, because Microsoft followed their pattern of the 80s and 90s, which is they licensed the technology. They didn't develop it themselves. They rebranded it as SQL Server. Again, that's where that comes from. In 85, you have a competing company called Informix that starts their own RDBMS. They have another flavor of SQL called iSQL in there. Skip ahead. In 95, Postgres finally decides to drop Quell. Not that, people have been just adopting SQL seriously. So for this project to continue and be taken seriously, they replace Quell with SQL. And that's the point where it looks very much like Oracle's SQL under the covers. And they rename it PostgreSQL, which is one of the two most popular open source databases. A year later, an open source company called MySQL AB releases MySQL, and this is why we're stuck with it these days. Wait. Yeah. All right. So now it's an issue of where is it used? The internet, small event you guys are lived through. So a quick review. In 89 to 91, a guy named Tim Berners-Lee that works at CERN, the guys that right now run the Large Hadron Collider, he works on an information system that he calls the World Wide Web. Okay, so this is over the internet. There used to be other protocols that were more popular at the time, but he felt those were inadequate. Like any good nerd, was rewriting stuff from scratch. So he wrote a web server called CERN HTTPD. Again, the name has been adopted since then by many other web servers, and his own browser called the World Wide Web browser. In 93, it actually starts getting popularized. Team at NCSA, which is another linear accelerator, I think, right? No?
National Supercomputer Applications Act.
Damn it. Thanks, Sai. So, familiar name, Mark Andreessen releases Mosaic, which becomes really the first seriously popular browser. Does anybody here know why it was the first popular browser?
It has pictures.
Yeah. Everything else before that was text. These guys came up with a crazy new idea called a GUI. So you could see the web pages rather than just look at links of text. That's a big advancement. Non-trivial. There was a lot of browsers in those between 90 and 93. All right, so like with anything good, commercialization starts around the mid-90s. 94, Andreessen leaves, hooks up with a dude from SGI, and starts a company called Netscape. They released the Navigator browser and a web server called the Commerce Server. Both of those have within it a scripting language called JavaScript. That's where that's from. A year later, Microsoft, finds out that they're behind the curve, releases Internet Explorer, the browser, and IIS, the server, and then gets involved into a nice little antitrust case thanks to the way they manage it. 1996, IIS through I think it's like NT4 Service Pack 4, something like that, gets a scripting language finally called ASP. And we'll get through that quickly. Other people that were not buying these commercial releases were a lot of times scripting through a thing called the Common Gateway Interface, CGI, usually using this language called Perl that started in the late 80s and was pretty popular with serious nerds. At the same time, around 95, you have a guy, Rasmus Lerdof, got his name right? Close enough. I apologize. Starts a little toolkit called PHP. In 97, it actually starts getting published to a wider audience. It becomes as probably the second most popular CGI language after Perl at the time. It eclipses it later. And then as a web server module, so it doesn't have to run through CGI and gets better performance. In 96, this is the problem. Java shows up. Promises to be the last language you ever need to learn. And they have an acronym called WORA. Who knows what that means? Anybody? Yeah, write once, run everywhere, run anywhere. That was a really nice marketing acronym. Java was still cool for a few years. Then a problem happens. In '99, Java 1.2 shows up. The marketing department doesn't like 1.2. It doesn't look nice, so it gets rebranded as Java 2. Java 2 Enterprise Edition enters the world, and then things start changing fast. So everybody needs an RDBMS to start with. Server-side engineers need a place. If they're writing any application that's worth anything, sort of, and really becomes like a website that's worth visiting, they need a place to store data. They're looking for persistent data stores. If they've had experience working in the 80s, or if they came out of college around that time, they would be aware of RDBMSs. And that sort of becomes a natural system to put your data in for them. At the time, again, that was a good, robust product you could trust. The fact that there's open source databases that are completely free, MySQL and Postgres, really accelerate the adoption, because all these startups start popping up as VC money starts flowing into this crazy thing called the internet and e-commerce. That was a big buzzword at the time. And because these are free and you don't have to pay licenses, they become like sort of the de facto what every startup uses. A small company called Yahoo uses MySQL. That helps a bit for its popularity. People there that have to deal with the scaling issues write a lot of books about it. So in the beginning, when people use RDBMSs, they are writing straight up SQL. Okay, they know SQL, they like SQL, they just embed SQL calls directly into the databases. You sort of extract the data into whatever you're using, an array or an object, and when you need to write, you write a bunch of code that basically will write it out to your tables. There's usually no ORMs or anything like it at the time. The concept of a persistent data store becomes conflated with RDBMSs at that point. A lot of times when I talk to people, when I ask them like sort of, when I talk to them about this thing, they are convinced that you absolutely need an RDBMS. When you're saving data, that's where you save data. There is literally no other alternative. And it just becomes this natural idea, like a data store, RDBMS are exactly the same thing, rather than being a type of one. All right, so this is a personal history of mine and many other engineers that worked in the late 90s. J2E loves patterns. One of the things, when J2E was announced, it came with this fucking marketing assault of technologies that are associated with it. XML, I had stacks of XML books, and then everybody spread the knowledge. If you happen to, during your electives in college, not take the software engineering class because you wanted to do something else like animation or whatever, you didn't know the secret that there's a crazy thing called design patterns. So it became this it was almost like a traveling salesman that's like spreading the gospel. You got your book, there was like J2EE enterprise patterns, and I have so many of those that I recycled over the years. It was crazy. There was a period where everybody was jumping on this. If you didn't know about it, you were reading them because everybody else was reading them, and everybody was doing it. So it didn't matter at that point. It didn't matter like really who you were. If you were a Java guy, it was sort of expected. Like, this is enterprise software. Serious people write a lot of lines of code. You measure yourself by your lines of code, not by performance or speed or anything. It's just like, I'm a dude that wrote 1 million lines of code, or 50,000 or whatever. And it was sort of like the more complex it was, the better. But the weird thing was that this was also invading like scripting people, like people that did PHP and Perl and Python. Like, suddenly we're all on the ORM bandwagon and patterns bandwagon as well. This is sort of where frameworks take off and where ORMs take off. Frameworks, I mean like MVC frameworks, and ORMs, the things. So the patterns that sort of made sense specifically to this issue that I'll mention later are the database abstraction layer. This idea that you don't have to write to a specific database, but just to a generic database. You had OR data access layer. I think the .NET world likes that stuff more. Data access objects were the specific mappers that write to your specific database. And then later, there's a thing called active record that is also influential. So there was just an enormous marketing campaign behind this. So my note, I put myself a note there. I'm going to take an example of like this fictional character. I'm going to call him Fartin Mauler. Okay, so Fartin gets tired of writing code, and then he also gets tired of being an architect. So he just settles that like the most profitable next thing for him to do is to start spreading the gospel of patterns. He writes enormous amounts of books and blogs about the topic, and he continues over the years to unearth new ways of getting everybody here more enterprisey. So you feel like I'm an adult. I'm not a hobbyist. I'm not hacking this for fun. I'm a serious adult and using serious technology. So the weird thing about him is that he's changed his mind many times over what is the right way to do things. But he was right before the change and he's right after the change. So he's sort of like, you'll read articles about ORMs are a stupid thing because now I believe in NoSQL, but also ORMs are kind of a good thing. It's really bizarre. Personally, I've read enough of his stuff for a lifetime. So the next thing that happens is, everybody and their grandmother writes an ORM. And the really bizarre thing, I must say, for me personally, since I've been doing this since '98, 16 years later, it's not stopped yet. There are, if you look at Wikipedia, just for a really sample, like a comfortable sample, you're going to see that there's over 100 published ORMs out there. The weird thing is that that's not even all there is. Like I wrote 2 in the startups that I was in. I did that as well. So you'd write your own. You maybe not publish it because you read it's about somebody else's really cool ORM. So now you're doing that, and then you become a true believer. And you start arguing with other people about the benefits of this, like why Spring and Hibernate, like which one is the right religion. It was a really bizarre phenomena for a while. PHP, which is a language I'm tracking right now because I'm working on the client for Aerospike for PHP, is literally still spewing ORMs. Like they are like erupting out of like the ether. It seems like it'll never stop actually. Specifically, like I'm looking at a pretty fun new framework called Laravel. That's like where all the cool kids are at PHP right now. It has its own new ORM called Eloquent. I just literally the day before was following that little Twitter shitstorm of people critiquing the guy that is behind Laravel called Taylor Otwell. And I got to read this quote because it was amazing. So this one guy, like while arguing with him whether his ORM sucks or doesn't, he was saying like, you haven't seen what I've been working on the last 4 years. Be scared, be very scared. I got to say, I personally am scared because this is not stopping. All right, so the main question is, should we be using an ORM to talk to the RDBMS? So there's some good stuff to an ORM for sure. CRUD operations, if you're doing a lot of those, if you're literally getting a record out of a single table over and over and over and modifying it, but basically looking at a single table, has a lot of repetitive SQL or DML, update statements underneath there. And ORMs kind of like get rid of that boilerplate code, make it a little easier to like not repeat yourself over and over with different models. Decent ORMs are also config free. All the active record variants out there sort of like don't need to have a giant XML that describes the schema. They just sort of look at the tables and they'll generate you stuff on the fly and learn relationships and such by like using foreign keys and all that. That's nice. Save some code. This is one of the weirdest statements I've ever seen because literally every time somebody says it, they always say, but this doesn't apply to me. So allegedly, ORMs allow non-SQL developers, there's such a creature, to work against an RDBMS blissfully unaware that they have an RDBMS under the cover. This is the statement. Everybody that writes about it actually knows SQL and writes about SQL and sort of like how they injected raw SQL. So I don't know who actually is that person. And decent ORMs cache data because RDBMSs are really not built to handle lots of reads and also not lots of writes. And if you could deal with the read problem, you can cache data and hope that you don't have any sort of caching issues. But a nice ORM is supposed to do that for you. Instead of going to the database, they'll go to like memcache or whatever layer you're using there. Okay, so I'm going to have several slides about the bad aspects of ORM because I'm biased. All right, the first thing is leaky abstraction. The notion that ORM support NoSQL developers is a hoax. All right, so the idea that there is such a user that is a non-SQL user, like literally that person is a unicorn. So I would say if you see him, grab him, rub his bald head, and ask him for 3 wishes because, I mean, that is a magical creature. I have never yet met that person. I literally, like if somebody sees such a person, tweet at me because I want to meet them and figure out how they're using an ORM but don't know any SQL. But I mean, literally, it has to be NoSQL. Maybe I'll put a bounty on this at some point. That term, the leaky abstraction, is attributed to Joel Sapolsky. What he means by that is that when you have not well-defined abstraction layers and you're doing not like complex stuff, so let's say when you're not doing CRUD, you're doing more complex stuff against your RDBMS, the implementation details are going to start popping in there. You're going to start seeing things like joins or wheres or all these weird SQL terms suddenly pop up in the ORM that's allegedly supposed to abstract it. So that's problematic. So when you use any ORM, and I literally mean any ORM, you end up with code that anyway looks like SQL. So this is an example from Doctrine. I'm not knocking Doctrine specifically. Literally all of them sort of have this problem in some form or another. This is the Fluent interface, which is sort of when any one of these methods returns in PHP this, so you can keep chaining them together. So it looks really cool. But if you look at it, this is a lot more concise. So all this garbage, lots of arrows, which each one of these is a method call too, is doing this trivial thing. And this is an example from the Doctrine page. It looks kind of absurd, but there's a lot of those on on their documentation. The next thing is I'm going to refer to the DBAL, the database abstraction layer. So this literally means you are going to work against this virtual lowest common denominator database that doesn't really exist. So it's a nice idea if you're writing really generic software. If you're writing a CMS and you're sending it out there and you don't know what hardware people have, it's really nice to use actually an ORM in there because you don't have to have MySQL or Postgres or whatnot under the covers. The other thing is, and I'm not knocking people because I was one of those. If you're a contractor and you have no clue what technology you're going to be forced to use, like usually you just come in and it's like, here's my database, it's SQL Server, or it's whatever. You usually will get used to using ORM code because it lowers cognitive load. You remember the one thing. You don't have to learn every single native client. You sort of learn this abstract layer and how to talk to it. And then you can go and do all sorts of weird, one-off jobs all over the place. I spent a year in Australia writing awful stuff that way. I don't know if I want to get into insults, but they're kind of funny. So popular database abstraction layers are kind of like politicians. They have to appeal to the dumbest database in the group. Okay, whatever the database is, if you're trying to find 5 of them, the one with the shittiest features, usually that's MySQL, is going to be the one that dictates what the features of the abstraction layer are. Because the problem is you can't, support it in any other way. And then usually when you talk to people who are behind ORMs, they're very authoritative. I mean, a lot of times they're very smart engineers and there's a lot of really complex code in there. So you just assume this the way, but like they literally will sell you on the one way to do things and it's gonna be their way, of course. The issue with the lowest common denominator is, again, you miss out on features that are specific to your database. All right, part of the reason of going over that prehistory was to show you every single one of those vendors that became somebody known today, SQL Server, DB2, all that stuff, they all had their own flavor of SQL. The standard came after the fact, and the standard just defined like a subset of what actually is out there. So each one of them has a different way of doing things under the covers. They're a little different. So when you're doing that, you're going to be basically missing on a lot of like optimizations that are specific to your database that you're going to use. It's called the abstraction inversion, when you basically have to rewrite stuff in a generic way that may already have like a real implementation under the covers. So, like a good example of that is auto increment. MySQL has auto increment that doesn't really exist in other databases. Other guys, like say Postgres, follows Oracle and they have sequence, and then sequence is a completely separate table that you talk to. So you're going to have a database abstraction layer that either doesn't know how to use this or sort of re-implements something that is natively under the covers. So that's sort of the problem with abstraction inversion. The other thing is abstractions really slow you down with all this extra code. It doesn't come free. Making an abstraction layer there's more code out there, that there's more execution time to get at your data. And then sort of the most insidious thing that people run into when they're actually in a startup and in production is the issue of functional dependency. So the idea is, let's say you are tied to a database. When you use an ORM, you're tied not just to the database, but to this other technology called the ORM. If either of those guys becomes obsolete, like now you got to worry about either of those becoming obsolete. It's not just like, oh, I'm going to switch databases if it like loses features. Now I got to worry about both, and you got to worry about bugs in both too. That's the other thing, and you got to keep track of feature development in both of them. And then literally the last one is absurd. I'm also curious at finding people that have had to do this. The idea that a database abstraction layer makes it simpler to switch databases. That it's like you just take out MySQL and just put Postgres under the covers. That's, yeah. I mean, does anybody here think that it's trivial to switch their production database as they have a web application?
It depends. Like on
I'm not saying if you have 10 users. I mean if you're like really being used.
it just depends what rules you follow getting up to where you are now.
All right,
If
yeah.
you didn't follow any, then no, you can't do it probably.
Yeah.
If you are using Aerospike.
Oh, no, it'll be a problem, but it'll be worth it. I'm sorry?
Where's the beef?
Where's the beef? I think there's some on the table there. But yeah.
No, I'm just saying no.
I don't, that,
So my point is,
Yeah.
I'm working on SQL abstraction instead of, it looks like shifting direction from NoSQL to SQL. Is that the point?
no, I think in general, I'm just going over ORMs. You can choose to use an RDBMS and not have an ORM. There's a lot of people that do that.
I know where so now there are lots of mature applications. They are capable of doing what you are talking about.
I know there's also a lot of mature applications that are extremely badly performing. Mature doesn't necessarily mean performance. Right, yeah.
They are high level code out.
Yeah, there's a lot of stuff that's been around for a long time. It's deployed everywhere, and it sucks everywhere. So, all right, I'm sorry, I'm going to keep going if you don't mind. All right, so the next thing is the issue of speed and resource consumption. So CRUD operations are straight up slower when you use an ORM. It's not that complicated. If you need to, again, have a bunch of code that goes and does it for you, there's more code in there, it's going to be slower. It's been measured in a bunch of different, there are people that have benchmarked this stuff. Using an ORM for queries, especially ones that join across tables, is even slower. Now, I'm going to guess most people have seen this live. Generated SQL is usually gets to a point where there's some hideous queries that are like produced out there, no matter like what the ORM is. Has anybody not seen really ugly generated SQL?
I think more importantly, it makes it really easy to do that stuff. So then I'm stuck cleaning up after some guy
Right.
who doesn't understand.
Right. Usually that's the point where they find the one guy that's really, really into SQL and have him write or gal, sorry, and have that person write the raw SQL sort of alternative to getting around it. It also takes a while to find it. Like, you know, slow query logs exist for a reason. But you don't necessarily understand where it came from. That's the problem. So again, if your ORM has problems coming up with the correct joins, and you sort of notice that early on, you're almost inevitably going to find lots of slow queries generated by the ORM that, you know, chew up the CPU, take up a lot of the memory on the server. And the problematic part is, like, if this is common and all your users, all the people coming to the application, the website, mobile app, whatever, talking to the API, get the same thing, it's going to become like a problem really quickly. The last example is ORMs really are sort of ask for crappy coding. Because they're so easy to use, because you allegedly don't have to think about SQL and like the impact of what you're doing, because it's like sort of abstracted from you, people start writing really suboptimal code. So the N+1 problem is like usually when you have like many-to-one relationships. A lot of times people will write them in a way using the ORM where sort of the many relationships that are related to this one record are going to be brought in a loop of separate queries. Sometimes people do this because it seems like that's an easier way to do caching. Because if you have to read each one of them, you can cache each one of them and then allegedly pull them out of the cache. But again, what you're doing is you're killing it, because SQL is all about joins and sort of making those really efficiently. And if you are, you know, reading individual, basically key value access in a loop, you're going to get horrendous performance. All right, some quotes. I didn't come up with any of this, so there's references to it. So this is High Scalability blog. I assume a lot of people here follow it. It's pretty entertaining and insightful. They have a lot of good interviews with people that have like serious scale issues, like, you know, Twitter, you know, Facebook, et cetera. There's a lot of information there about scaling. ORM frameworks are built to serve as wide an audience as possible, and while their success is unquestionable in a commodity middleware market, they're not and cannot possibly be tooled to accommodate the atypical demands of high scalability architecture. Next, this gets nastier over time. So this is Laurie Voss, CTO at NPM.js. I want to be very, very clear about this. ORM is a stupid idea. These are only 2 gems that I pulled out of that article. It's pretty lovely. It's slower than just using SQL because abstraction layers always are, but unlike other abstraction layers, which make up for their performance here with faster development, ORM layers add almost nothing. The link is there. Next, this is an article called Bad ORMs, definitely worse than bad SQL. As more developers use only ORM to create applications, they lose their touch with the database interactions, the queries behind it, the reasoning of why to use a certain kind of query, the performance impact of an inner versus outer join. Yeah?
I would have to say that most developers never had a touch with it.
Really?
I don't know.
I might be really old.
I think it's one of those things that
Right.
developers don't seem to get.
Well, I mean, SQL is its own language, and it's extremely good, and it's very certain use cases. Not necessarily for web applications, though. But you're right. Yeah, I talk to you later about it.
I mean,
Over a beer. I need a beer.
If you look at Node.js, for the longest time there was like no way to connect to my SQL front.
Right.
And so I think there is a kind of newer generation of
Yeah.
people who might not have much experience.
Right. Now, this is literally one of the best articles about this. Since it's gigantic and it's really more like a research paper, I'm going to only quote the title. It's been referred to by other people like Jeff Atwood from Stack Exchange. Object-relational mapping is the Vietnam of computer science. That is an excellent, excellent article. It goes really in depth into the details of like what is the problem with actually trying to write an ORM that works and doesn't have problems. But I also like it's an extremely awesome bit of trolling. All right, so we're getting to, I don't know, beef or beer or something. Is an RDBMS the right data store? So really the question is, do you actually need an RDBMS? So the majority of ORMs out there, they're tightly coupled with having an RDBMS as their data store. There's not a lot of them. There's some out there that are like data mapper, which became Ruby object mapper, that are like more abstract. They don't necessarily assume you're going to have a SQL sort of query language under the covers in an RDBMS, but most of them do. When it comes to actually the idea of can you map objects to the relational model, there's a thing called impedance mismatch, which is sort of the research behind why this doesn't work. So this really talks about how the philosophy and the implementation details of object model and the relational model just doesn't fit. It's a really big topic, and I'm going to really cover it really lightly because you guys can read on it separately. It'll take forever. So OO notions like encapsulation, okay, inheritance, polymorphism, they just don't map to RDBMSs, right? You can see all the data. There's no way to hide anything from you within it when you're using it, if you have access to it. And views don't count. Okay, there's a major difference between the data types that are supported by an RDBMS and the ones that are supported by objects. So usually, not usually, RDBMSs are scalar data. You have things like strings and ints, floats, flat data. Okay, the tables are two-dimensional. There's no way to actually get any depth in them. The difference is that objects, they'll usually have things like, lists, maps, sets. They use different, more complex data types, and those just do not map well. The manipulation of data in objects is imperative. Usually you're operating on things like lists and maps under the covers. And in RDBMS, it's declarative. The transactional difference, this is actually pretty huge when it comes to like sort of consistency of data, is that when you're changing data in an object, you're usually doing it through a set or a set operation, and it's instant. Like it's basically on every attribute can be modified by a call, and at that point, the object has been modified. In the case of RDBMSs, usually you're using transactions, and if you're not using transactions, you're just changing one record. You're usually doing multiple fields at once, and you're doing it in a delayed fashion. So there's this whole difference between when to persist, like when do you actually persist changes? Like there could be cases in a web application where you're starting to change attributes. If something happened, like the process died or whatnot, it's actually not going to be persisted, right? You need to sort of do it all en masse for it to work for an RDBMS. A lot of it has to do with literally the way it was designed because of just inefficiency of being able to update specific cells. If RDBMSs, again, come out of the 70s, they have limitations of what computers could do at the time, and it would be insanely inefficient for them to just change single cells all over the place. They're built to do multiple things at once. All right, this is something that, again, anybody who's made a RESTful API that has to talk to whatever, like mobile applications, like mobile phones, applications that are widely distributed, knows that the normalization is the bread and butter of the relational model, is going to kill your web application. If you're going to be sticking to what Cod wrote, your thing is never going to actually respond in time. So again, if you don't know what first, second, third normal form, what Boyce Cod normal form is, read up on it. It's interesting, but probably has no application for your web application. So the goal in the 70s and the 80s, when normalization was formalized by Cod and then Boyce, was that data was supposed to be as small as possible. Okay, drives were extremely expensive. Actually, storing data was super expensive. I had a drive in the late 80s that was like, 40 megs, and that seemed like the hugest thing in the world at the time. And commercial databases had drives that are just ridiculous by today's standard. So data was storing data was extremely expensive, and the more normalized you got, the more compact your data was. You didn't have repetition in it. The goal, since the World Wide Web has started, the 90s, and then when web applications like Gmail and Google Maps start popping up, is all about speed, because people will not wait for your 2-3 second query anymore. Literally no web application is open to a wide audience like an API that's supporting a mobile app or anything that's out there. I'm not talking about an intranet that's for like 20 people behind a firewall, but stuff that's out on the internet is even in third normal form. They've been denormalized out of that. So web applications quickly devolve to lower forms of normalization. Everybody does it. You're going to repeat data into your table because the holy grail is to get to doing this with a single table access and not need to do joins. RESTful APIs specifically are the most common thing now, and every sort of web framework supports them. They are essentially always single access. You'll have a resource and an ID. It's like in your RDBMS, it's going to be a table and a record in it. So there's no joins usually involved in any of those things. All right, so what should you use for your application? So I promise this is almost the last slide, or I think it's the last slide. The question is maybe you actually need a key value store. So I am biased. We are a key value store. Just to throw in other ones out there, there's also Redis. That's a key value store out there. Usually key value stores support complex types of data. Like Redis has been described as like a, what was it? Has a specific term. It's like the data structure engine or something like that. So again, don't go generic. Don't try to use a database abstraction layer or an ORM and expect to get actually performance out of it. Like it's either there to make your life easier or it's there to be performant. It cannot be both of them. If you choose a specific database, be really aware why you're choosing it. Like if you're choosing MySQL over Postgres, really know what its strengths and weaknesses are and code to those. Use, maybe you want to minimize your abstractions and actually use the native client of the database of your choice that you made a conscious decision and use it in the best way possible and the most, the best performance possible. If anybody looks at the code that's under Wikipedia, which is written in PHP, they use MySQL, they use Postgres, and they talk directly to those guys. They don't have layers and layers and layers up there. But again, because they have a serious scale issue. So you got to be positive about the fact that you're going to have a scale problem at some point, and maybe you want to think about it in advance and actually write towards performance. Key value stores are a lot more natural way of modeling your data. So on the web application side, if you're using PHP, you use objects or you're using a lot of arrays. Okay, and arrays are basically associative arrays or key value pairs. If you're using Python, you use a lot of dictionaries. If you're using Ruby, similarly, a lot of the data is actually an object that is like a whole lot of key value data in there. Key value stores are built to do that naturally. They don't have to do all sorts of goofy things that relational databases have to do. The support for complex types. When you have a key value store and it natively support things like lists and maps, what that means is that you don't have to do crazy things like joins when you have a many-to-one. So for example, if you have a table that is the user table, and users have credit cards, okay, so users can have multiple credit cards. If this was an RDBMS, this would have to be a separate table called cards, and there would be a foreign key, or maybe you skip it because you're going for speed here. But you would have to do a join across to get all the cards of a specific user. In a key value store, you literally have a bunch of cards. You'd have a field called cards. It would be an array, and that's it. They're all in the same row, basically. You don't have to do a join. The whole idea of you need to have something that can translate joins for you is only if you're stuck in your head that you have to have an RDBMS under the covers. If you have something that supports complex types that is not two-dimensional and only scalar data, you can basically put those guys in there automatically. Yeah.
So what if you just would stick to your RDBMS and then denormalize your data there and use it in a NoSQL style?
Yeah.
And also use maybe JSON to introduce any
Right.
structure.
You could do that, but the only problem. So you got straight to the next point here. If you are using your RDBMS as a key value store, it's literally all denormalized into one table and you're just accessing, stop, seriously. You need to use something that actually is built to do this. RDBMSs, if any way your application has denormalized its way and devolved back to the Stone Age where everything is just a single table, it's a shitty key value store. It's extremely slow compared to Redis, compared to us. If you're using a document model, even Mongo that is slower than us, way faster than MySQL when it comes to grabbing a single sort of denormalized object out of there. So you could use MySQL. Again, it's like, you could use a jalopy in a car race, but it's probably not going to win the race. So it's just literally RDBMSs end up in most web applications exactly being used that way because people are like, well, it sucks. I'm going to get rid of the joins. I'm going to denormalize. But then, it's cool. And it maps closer to how your actual data is, but it's just extremely slow. I mean, we're talking about orders of magnitude difference. Let's say if Mongo is 10 times faster than MySQL and we're 10 times faster than Mongo, that's a lot of difference there. If your database is fast enough, you don't need a thing like a cache. Okay, so a lot of times in the, say, again, PHP land, but this applies to every single sort of dynamic language out there. You have a slow RDBMS, you throw a bunch of memcache servers in front of it. You make a cluster of them, okay? If your database is actually as fast as that cache, you don't need that layer. So first thing, there's hardware involved, there's software involved. That software might have bugs. It costs too. Like you need to have extra instances that are just MySQL, or at least to give some of the CPU and the memory on each of your web nodes to that. It also adds a lot of complex caching logic in there, because there's the whole like, okay, is it in the cache? Let's build a cache key, and if it's in the cache, if not, I'll go to the database. If I find it in the database, I'll put it in the cache, and then there's this whole issue of like, do objects expire? I mean, it's only until recently where people came up with decent algorithms about how to get caching objects that don't cause like a mismatch between in the data, right? Cache expiration used to be a really pain in the ass. There was some good articles that the guys from Basecamp wrote about like Russian doll caching and timestamp based caching, but still, if your database is as fast as a cache, just get rid of all the cruft. Like make your stack smaller and make your code inside your application smaller. So again, this applies to the whole idea of like, I love my ORM because it has built-in caching. Well, use the right database. You don't need that ORM. That's the one feature that it has that is really cool. You don't need it. So in general, the idea of simplifying your stack, we're talking about both on the hardware side, having literally like a web server and having a database cluster behind it and nothing else. Your application logic, you can remove caching out of your application logic itself, which is really convoluted. If you look at a lot of ORMs, it is crazy spaghetti code in there for every single model. The last one is a term that we came here over lunch or beers or I don't know what, and we keep repeating it because it's offensive. Don't shard yourself. So RDBMSs are not built to deal with web scale applications. Yahoo ran into it with MySQL. Lots of people made their fame over being able to figure out some half-assed way to cluster MySQL. A lot of times it's done by sharding. What you do is you'll take like some hash function and like identifier for the resource, and you'll run it through that, and then you're going to have multiple databases behind it, and you're going to send different people according to hashing to a different node. It's an awesome idea, but it's one of those weird engineer hobbies of like, instead of focusing on your application, you're going to procrastinate and fix MySQL, or you're going to procrastinate and fix whatever the hell it is. People wrote all sorts of crazy code to get memcache to cluster, to get MySQL to cluster. It is crazy ass hacks. Usually it's done wrong. So the one place where people usually make gigantic mistakes are they use the wrong hashing function. And you're going to get uneven data. If you have 3 nodes, one of them is 10% full, the other one is 30, and the last one is 70. Let's say you were really clever and you did some hashing function on a username, but you did it really, really trivial. Like you went, the first third of the alphabet is going to node 1, then the next, then the next. There's just not a lot of Xanders out there. There's way more Michaels and Jasons. So you're going to have one node that has a ton of data, and therefore it's also going to have relatively the same amount of load. And when that node starts overheating, you get a hotspot, the entire cluster melts. That's happened to people that, when Foursquare, I don't know, it was like 2008, 2007, something like that, when they were trying to do that with Mongo, they had regular, like the thing would just fall down regularly because they would just like shard incorrectly. So let's say you're using somebody's middleware that shards for you and is really clever, okay? There's other problems there. What happens when one of those nodes goes down? Who is there to actually make sure that you can access the data? Or where, what do you do? Where are replicas? So that's another problem. Then there's other issues of like, let's say you want to add a node now into the cluster because like you can afford a 4th machine now. You're going to have 3 machines that are pretty full and 1 machine that is completely empty. If you want to now rebalance the system, you've got to also write your own code to go read all the data while this is in production and move stuff around. And this is not trivial at all, okay? What is the last one? So, and then the last one has to do with configuration. Again, when you have if people here have experience with Memcache clusters, the problem with Memcache is a lot of times if it gets a little overloaded on connections, it's just not going to answer for a while. So this node may go down. You need to actually, your configuration in your application has all the IP addresses for all the nodes in the Memcache cluster. But one of them is not answering. You actually don't, you need in your own application to write fallback behavior for what happens when one of those nodes is not answering. And again, this should not be the job of the person who's trying to make a certain application. Like focus on your application and choose the right tool. So not to beat the war drum too much, these are problems that we have solved. Aerospike is not just a key value store, it's also a distributed database, and it's been one from the ground, sort of from the ground up. So actually, we have a lot of information on this, yeah. Go ahead.
But you mentioned problems of partitioning and scaling.
I'm
but
sorry?
this is also in NoSQL. If you try to do this on an Hadoop cluster, you have the problem or a balance.
Oh yeah, Hadoop has massive problems. So Hadoop, for example, its main problem is this concept of the name node, right? You have one thing that tracks where all the bits of all the files are actually distributed, right? They're distributed across the entire cluster. If that name node goes down, there is no cluster, right? That's the first thing. You have to constantly have backups and hope that that thing, doesn't run out of memory too. Because that one box that it sits on, it's bound by RAM, right? There's going to be a point. This is why the blocks are so big in Hadoop. Because if you had more of them, if it was more fragmented, you would need to have a bigger hash table. You'd literally run out of memory, and you reach capacity because of the limitation of the name node. So the name node is one place where this is a distributed system, but again, it's just not written correctly. In our case, there. The secondary name node only helps the name node with certain operations.
I understand. That is the downside of master-slave architecture. What's your take on peer-to-peer architecture like Cassandra?
Or like us?
Oh yeah, or like yours, yeah, whatever.
Yeah, so I can give when it comes to clustering and being able to grow horizontally, okay, so again, RDBMSs, sorry, I'll get to you in a second. RDBMSs were designed for vertical growth. You got to the edge of your capacity, you just got bigger iron. You got a bigger box, had more memory, more expensive SANs under the cover, whatever the hell it was, that was the way to get around it. That has a problem. Growing in RAM is problematic, and growing on one machine really just doesn't work. It hasn't worked since the late 90s. And like what Google and Yahoo saw in the late 90s is nothing compared to what they see now. It's nothing compared to what Facebook and Twitter see. And if you're lucky, your application as well. In the case of such a system like Cassandra or like us, there is no master. Okay, when a node joins into the cluster, when it basically broadcasts that it's ready to join the cluster, in our case, you're going to have the existing nodes take a vote over how they're going to redistribute their partition space. The algorithm is Paxos. You can look it up. There's been a lot written about it lately. We have a person in the back here that's really good at implementing it, Sai. It's definitely not a simple algorithm, but the idea is one of the nodes in the existing cluster becomes the leader, and for a very quick period of time decides which node has what part of the partition space. When that happens, the new node joins into the cluster. This, in our case, that usually happens in around 50 milliseconds. Now you have a new node in the cluster. The existing nodes are going to take stock of the records that they have. We call rows records, whatever, just to make things complicated. But basically, let's say the rows that are in each of those nodes, they're going to go over them. And if they don't own them, they're going to ship them to the correct master. Okay? So there's going to be master partitions. There's going to be master data, and there's going to be replica data in each one of these nodes. And they're going to be shipping it around until basically very quickly all of the nodes get to an even level, which again avoids the hotspot problem that I talked about earlier. Yeah?
I had a pressing question just for the slide before this. Is key value store an answer to an OLAP application?
Is a key value store an answer to an OLAP application? I don't know, I've been thinking about it a lot lately.
And also, I think I'm not sure if it's,
So
you conveniently missed the columnar databases which grew out of that, the history which you actually described earlier.
Right.
There are columnar databases, which again, Stonebreaker started that.
So columnar databases are fairly new, number one. A lot of times, all those ideas come out of all the NoSQL databases and all the changes, the non-RDBMS databases, pretty much all come out of large internet companies that have seen crazy data in the late 90s, early 2000s, have had the official solution die on them, whether it's Oracle RAC with a bunch of really expensive $1 million SAN underneath, and just buying top-of-the-line stuff because they had VC money, their shit's going well for them, Yahoo, Google, and stuff still fell over. So a lot of these guys wrote their own NoSQL databases as a way to get out of this, or used some obscure NoSQL databases and used them internally because RDBMS just did not scale. So columnar stuff like Bigtable comes out of there. Vertica comes later. Vertica comes a lot later. So you have things like Dynamo and all that, and then Cassandra is based on Dynamo. Hadoop is based on Google File System and Bigtable. So a lot of these ideas come out of like what is released out of these large internet companies. Vertica, obviously Vertica was a sort of a school project that Stonebreaker once again took to commercialize. It still has problems. I mean, it does certain things like analytics fairly well. I know because I tried using it at a data warehouse before. But it has its own issues, and I can talk to you over beer about it.
Recommend a key value store for an OLAP application?
Yeah, I don't know. A lot of times, in that case, people that have a lot of really high read and write requirements that use us in conjunction with things like Hadoop. Okay? So a lot of times they will be running, like sort of constantly churning through analytics and updating the database and use a key value store as a front end that the web applications talk to. I didn't go into that because that's like a whole different topic. I did a meetup in Tel Aviv in December to talk about that. It is an hour-long thing. Specifically to the web application world, where you're doing things like a RESTful API, and you're getting resources by ID. That's not an OLAP situation. It's a little different. But in the case of an OLAP system, though, a lot of times, in order to make queries happen faster, you know that people do use aggregate tables, right? They will basically pre-calculate a lot of the stuff. And pulling that pre-calculated data out of MySQL is a lot slower than pulling it out of a key value store. Again, I know that because when I was working at Accelerator, it was very hard to keep the system running with the biggest MySQL instance that I could come up with. Yeah?
You mentioned that there is this Paxos algorithm, I don't know. But you basically cannot end up having a not node as well? Because you pre-partition, right?
Yeah, we are.
So how do you solve the problem?
In our case, we're pre-partitioned, but the idea of the pre-partitioning just has to do with which node, knowing in advance which node owns the record.
Yeah, but
so,
if I don't know beforehand which record I get.
Aha! Okay, so again, this seems trivial, but there's a lot of thought that goes into it. So in our case, wait.
What do you do? You repartition, you redistribute?
Nope, the partitions, basically again, like I said, when you have this vote and a new node comes in, you do repartition the space. Okay, so each one of them now has a different set of partitions. They will go over their data, and if they don't own it anymore, they will move it to the correct owner.
Okay, this is for the existing data. I get another.
Oh, you're talking about from the application side?
How do I rebalance? If I get a new partition that doesn't.
So there are no new partitions. There's always a set amount of partitions. And every time a node drops or a node joins into the cluster, the table space is repartitioned. And it's extremely fast. We're talking about several milliseconds. So on the application side, okay, in our case, we have a client that doesn't just do TCP/IP. Okay, it's not like, say, a MySQL client that all it does is keep a connection pool and send data and get it back. Okay, yes.
Well, the only thing I would say is that there is a level of indirection here, which is that there are usually 4,096 partitions, but where those partitions reside is flexible, and our system handles that. So depending on how many nodes there are, 1 over the number of nodes is the number of partitions, percentage of partitions that will be on each node, and it will redistribute it there. So you don't, it doesn't accumulate.
With time and you remove more partitions.
Yeah, you bring in a new node, and then n plus 1 is the divisor, and then each one so this client is saying knows about the indirection, not where to find it. So just because your partition number 2000 doesn't mean that you're on a specific node. That is dynamically changeable.
All right. Yeah. Sorry.
How does this system handle prioritization operations?
Okay, so in our case, correct me if I'm saying anything wrong. So in our case, key value operations are always prioritized. They are the fastest thing, regardless of what happens. Things like scans are going to be slower because they just take a lot more. So that you can control it. It's configurable how it behaves. But reads and writes, like single reads and writes to get specific objects out are going to be a lot faster. So to get a record, basically to get a row from this denormalized table is going to be the fastest operation that you can get. And we're talking about sub-millisecond operations. Okay, so in our case, most of the operations are sub-millisecond. And we have sort of very predictable low latency. So there's not going to be periods where suddenly you have this giant spike in latency and it's like doing whatever. I'm doing shit. Don't talk to me. Like our database doesn't work that way. So things like rebalancing, for example, this taking inventory and shipping things off is also a lower priority thing. So it's happening in the background. So to mitigate that, okay, so to mitigate it on the application side, like I said, our client is more sophisticated than usual clients. It knows the partition map in advance. There is no master node you gotta go to ask like, oh, where do I find the data? The application itself basically passes a record, when it does a put or a get, it has a key. Okay, this key, the client knows when it hashes which node it goes to. Okay, so first thing on writes, let's say the problem time is when you're doing this new node comes in and rebalancing. So let's say there's a new node. Writes happen automatically because even if it's a completely empty node, the write can just go there, no problem there, right? So so by the way, this happens within less than a second. Okay, the client knows that the cluster has changed in less than a second. It has a very lightweight thread that checks, basically compares like a hash that represents the ID of the cluster. And when a new cluster joins, it just generates a new ID. And it just says, oh, this string doesn't match this string. I'm going to ask for the partition map. Okay, so this happens in a very short period of time. You don't have to change anything on your application side. There's no configuration change because you're talking to a cluster. You just have a DNS. You don't have an IP address. You have like a DNS that you're talking to. Usually, that's how you configure it. So whatever happens in the background, how many IPs you got, it doesn't matter. It instantly knows where to write to. So reads are a little more complex because the new partition owner, the new master of the partition, may not have that data yet. It may not have been shipped over. So the first thing it's going to do is going to go talk to the correct node. And if it's not, it's aware of where the old owner used to be, right? And it'll fail over to that. So if I'm trying to talk in now I know it's supposed to be in node 4, but it's not there yet, I'll go back to node 2 and get it from there. So this is part of how you don't have to have any of this logic on the application side because just like on the server side, sort of with minimal configuration, the cluster just grows or drops or whatever, changes its size without you needing to think about it. You don't need to have a chef push to change your IP addresses on your config file. On the client side, you don't need to have any sharding logic because basically your client is aware of where everything is. And even as it changes, it dynamically downloads this, pulls down the data. Again, it's extremely fast. And it knows where the data is going to be now. So this is a high availability system that can basically, we have people that work at insane loads. Like okay, I'll mention one customer, AppNexus. They're, I think, second after Google in scale of ads being served. They have a cluster that's, I don't even know how many nodes, but a very low number. Okay, we're not talking like Cassandra here. We're talking about in the under 20. They serve about 4 million operations per second, reads and writes, and they've been up for 4 years continuously. So the way, for example, we deal with software upgrades is that we usually will do a rolling upgrade. We'll change one node. It'll drop out of the cluster. You upgraded, then you bring it back into the cluster. You drop the next guy, et cetera, et cetera. The cluster itself never stops because there's always replicas somewhere, right? So because we have some of the data is replicated, even if the node that is now the master came down, its replica is somewhere else, and we're now shipping it around, and there's going to be, it's going to be replicated again, et cetera. So this is the way that we basically the cluster itself never stops, even though nodes can drop out of it. There's a lot more to this. I really want to get to a beer, so.
Yeah, I have a quick question. How do you improve eventual consistency? Because it's a NoSQL database. And the other question is a follow-up question is, what is your current auto-scaling strategy? Auto-scaling strategy.
So auto-scaling, I think I just explained.
Yeah, but I'm talking about in terms of real-time auto-scaling or close to real-time. You mentioned your system is capable to do live migration, self-healing or things like that.
Yeah.
But I'm talking about automatically scale out your cluster in very, very short time. Scale out like double the size of your cluster or triple or whatever,
In theory, you can have 5 nodes and you can bring up 5 new nodes. It doesn't matter if you bring up 1 or 5 or 100 new ones.
I want to make them be functional right away.
They are functional right away. So like I said, because of the way this works, the client now knows that, let's say we went from 5 to 10 nodes, okay? The client, like I said, this is an automatic process. Rebalancing is automatic. So again, the client is going to assume first thing that it's going to go to the new owner of the data, the new partition master. If the data is not there, it'll know to fail over to the old owner.
Actually, that part
Proxies.
Proxied.
Okay. Right. So sorry. The server will basically ask the old owner on your behalf. Okay. So again, this is something that is like it scales very fast and very easily.
So is that at second level or microsecond level or millisecond level? What kind of
millisecond level? Yes. The Paxos vote is around 50 milliseconds, right? Sort of, depending on size of data, et cetera,
right.
or whatever.
Yeah. I'm talking about realistic size of cluster.
Yeah, we're talking in milliseconds. Yeah.
All right, so I'm curious to hear your take. I get the ORM thing. There's a lot of caveats, and but one thing that hasn't been addressed in this session is in SQL land, in RDBMS land, you have constraints, so that when inevitably you or someone else tries to reference or insert a record that doesn't exist, but says there should be a foreign key, then it will fail. But then in these NoSQL stores, you don't really get that guarantee.
Yeah, I mean, we have policies for write operations that you could emulate a SQL system fully. You can say, I only want to insert if this is a brand new, which is like a create. I only want to change data if it already exists, which is like an update. I only want to do something that looks like a replace. So the default behavior, let's say on the PHP, Python clients and such, is more to make it feel natural, like an array. Okay, so when you're adding a key to an array, right? It's just sort of, if it's not there, it shows up, right? Let's say you had a key value pair A, is 1, it'll just pop in there. If there was an A and you changed the value, it'll just overwrite it, right? If you had a scalar type like 1 and then you're dropping an array in there, it'll just become a complex type. So our database is out of the box. This specific client is configured to behave like that, to feel like this is basically you inserting data into an array. Okay, but you can completely change it. We have write policies that give you full control over. You can make it. You can be very granular and say like, yeah, I don't want to overwrite data at all. Like I don't want to behave like an array. I want to be like, if there's a collision, fail back, and I'll deal with it. Now, the way we deal with it, as opposed to say in ORM, is like a lot of times, this is pretty procedural. Because it's so fast, you can have a kind of catch block or a, if bad case happened, that'll change, decide on some other logic. These writes and reads are so fast that you can afford to do this. It's not like you're running like a 2-second query again. We're talking about millisecond operations.
All right, and then I have one more.
Just doesn't like you.
So have you heard of Foundation DB?
Yeah.
So it's basically Foundation DB is a key value store, but then they also have this SQL layer that they've built on top of it, and so you get a lot of. I think in a lot of ways it does change the game a bit because
could be.
They also impose rules on you, like no queries over 5 seconds, and so. It does seem like something that can scale.
So again, imposing rules, again, timeouts, we have timeouts per operation. I can have read timeouts, write timeouts, and all. When it comes to Foundation DB,
so I'm not saying that you don't do it.
No. I'm just saying my take on Foundation DB is like we used to be before June. Foundation DB is magic. It's closed source, so however it does it, or whatever the benchmarks that are put out, are basically magic because you have no access to actually looking at the code or running it. Yeah, but the database itself. Yeah. So I have a hard time commenting about it.
So you guys, can we inspect your source code?
Yeah, we're open source. Go to GitHub/Aerospike. You can read anything.
You're almost new, probably less than a year.
Yeah. Yeah. That's still a lot of code. I mean, you can start reading it now. It'll take a while. I still don't know all the server code, or very little of it actually. Yeah. It is, man, so many lines. You feel like really accomplished. All right, does anybody else have any questions? All right, cool. Thank you for coming and for listening to a tedious, long talk. I'm sorry, I should have timed this a little better. If you have any questions about Aerospike, the server or the clients, anybody have feedback on the PHP or Python side, personally to me, I can give you my card and let me know how it's working for you. And that's it. See you guys around the next meetup.